Hello, everybody. It's me, Joe Biden. I'm going to prove Sylvester's criterion of inertia, which is a cool linear algebra result. So Sylvester's criterion says, let phi be a symmetric bilinear form. It is. Phi is linear in both of its components, and phi uv is phi vu. Then there exists a basis v1 up to vn for the vector space such that phi is represented by the matrix with the identity of size p, minus the identity of size q, and the zero matrix for p and q non-negative integers such that their sum is the rank of phi. This is related to stuff like in special relativity. The Minkowski product is given by the symmetric bilinear form represented by the matrix with minus 1, 1, 1, 1 on the diagonal in units where c equals 1. This matrix is unique. First, we will prove the existence. We know that phi is represented by a symmetric matrix, so we can diagonalize it, and therefore there is basis v1 up to vn such that phi vi vj equals lambda I delta ij for some lambda 1 up to lambda in R. Without loss of generality, we can reorder the lambdas so that the positive ones come first, then the negative ones, then the ones that are zero. We define ui to be the square root of the absolute value of lambda I if lambda I is not zero, otherwise set it to be 1. Now define vi equals 1 over mu I e I, and this basis works. Now, the second part of the theorem is also that it is unique, so let's get to it. No, the rank of phi does not depend on the basis, so it's sufficient to show that p is unique since p plus q equals the rank of phi. We want to show p is the largest dimension of a subspace if v such that phi restricted to that subspace is positive definite. First, we show we can find such a subspace. Suppose phi is represented by one of these matrices with respect to some basis. Then phi restricted to v1 up to vp is represented by a p, so phi restricted to this is positive definite. Now suppose capital P is any subspace of v such that phi restricted to it is positive definite. To show p has dimension at most p, we find a subspace complementary to it with dimension in minus p. Let capital Q be spanned by EP plus 1 up to Vn. Then phi restricted to this is represented by the matrix with minus IQ 0. Now if V is in both P and Q and non-zero, then phi VV is greater than 0 since V is a non-zero element of P. But it's less than or equal to Q since it's a non-zero element Q. This is a contradiction, so P intersect Q is 0. Now you can compare the dimensions of these and show that the dimension of P is less than or equal to P. Similarly, we do that for Q.